there's even more we can say about the graph of this function. Okay, so let's look at it just a little differently. For large x, the numerator is, well, this, we know what the numerator is. And we expand this. X minus 1 times x minus 5 gives us x squared minus 6x plus 5. Multiplying that by x plus 3, we would use the distributive law, write it out carefully, but I believe this is correct. Okay, we get x cubed minus 3x squared minus 13x plus 15. If x is equal to 1, we get 1 minus 3 minus 13 plus 15. The negatives add up to negative 16. The positives add up to 16. It's 0. We could check to see if it's 0, 3, and also 5. And if it is, then we've multiplied correctly. Okay, so there's our numerator, and we've expanded it. Okay, now, if we had the numerator in expanded form and want to ask ourselves what happens for large x, well, let's just see what happens for x equals 100. For x equals 100, the numerator consists of x cubed, which would be 1,000,000. 100 cubed is 1,000,000. 100 squared is 10,000, and 3 times that is negative 3 times that is negative 30,000, which is kind of a big number, but it's nowhere near as big as 1,000,000. 1,000,000 is over 30 times bigger than this. And then 100 here gives us negative 1,300. 15 gives us 15. Okay, this numerator is close to 1,000,000 because all this stuff over here is not very significant in comparison to the million. So we've got a numerator close to 1,000,000. Similarly, you can do the denominator. Okay, the denominator is x squared plus 5x plus 3. Square 100, you get 10,000. Multiply 5 times 100, you get 503. And that's not very significant compared to the 10,000 that you get. And if you do large negative x, you're going to get similar results, although your results will be negative. So what happens, though, is that the numerator has a value close to x cubed for a large value of x. Everything else becomes insignificant. Okay, all the other factors. Okay, all the factors when it's in this form are insignificant compared to the x cubed, provided x is large enough. And the denominator is close to x squared. Well, what's that mean? That means that our function, which is written here and expanded here, has to be close to x cubed over x squared, which is just x. So for large x, y is approximately equal to just x, which means that we can take this graph and we can draw the line y equals x. And for large x, the value of y has to be close to the value of x. So that on the right side, this thing's going to go up, and it's going to eventually, I'll just run through my stuff here, eventually going to tend to become asymptotic to the line y equals x. On the left, the graph will be asymptotic to the line y equals x. Now, that's going to force me to redraw this curve, which has the right general idea, but in order to be asymptotic to this thing, to this line, it's most likely going to lie below the line. That doesn't mean that it couldn't come up through the line, be asymptotic, come up through the line, and then come back down. It's another possibility that we're not going to analyze, is that it could come up like this, come up somewhat, and then go down. So either of these is better than this, because of course this isn't asymptotic to the line y equals x, but when I drew this, we weren't considering that the asymptote would be the line y equals x. So I can draw, I can kind of blur this out, but I don't have much choice about leaving all the chalk there so you can see where it was. But maybe a little lighter than that still looks like a... Okay, so it's going to be one of these behaviors, either like this or like this, and we can tell which one it is by further analysis, but that's as far as we need to go in this course. Now be sure you understand this. What we've demonstrated is a rule that you see in your textbook, and your textbook does a good job of giving you reasons why this is so. The rule is simply that only the leading term, the highest power term in the numerator and denominator, matter when you're talking about end behavior. So you can just throw everything else away, take your highest power term in the numerator, your highest power term in the denominator, divide them, and you get an asymptote. Okay? Now that asymptote in this case is a linear function. The asymptote, if this was x to the fourth over x squared, you'd have x to the fourth, x squared here. So the function would be asymptotic to a parabola. If you had x cubed over x to the fourth, you'd have 1 over x. So the graph would be asymptotic to the graph of 1 over x as you approach positive or negative infinity. Whatever happens with the zeros in the vertical asymptotes happens closer to the origin than your end behavior, because remember, end behavior is evaluated by considering positive or negative values of x that far exceed the most extreme position of a zero and asymptote on this side or this side. So you use large x, and then the behavior for small x, and small x being anything in the vicinity of the zeros and vertical asymptotes, we'll have to articulate with the large x behavior, and we'll modify the large x behavior. This graph is nowhere close to the graph of y equals x when we're between about here and here. But as we go further away, it becomes close. When the graph approaches a slanted line as an asymptote, we call this an oblique asymptote. So we could say that y equals x is an oblique asymptote. Oblique meaning not straight across, not straight up, at some angle with straight across and straight up.